let's start the lecture. So today's last lecture, yeah? Okay, so let's look at the couple of phase diagram in slide here, and also we're going to look at the Gibbs phase rule, so-called Gibbs phase rule today. And then if everything finish in time, I'll go over, we'll do the actual overview of the thermodynamics, what we have learned so far. And especially I'll just tell you what is the most important thing, at least you have to remember, what you have to capture from this class. Okay, so this is, in the material science, this is the most famous phase diagram. Iron carbon binary phase diagram. This is the most phase diagram. It's not because iron is most abundant actual material we are using among the metallic system, but actually this system containing most of the invariant reaction we have run, and also the phase transformation is very interesting here. So let's look at this phase diagram. So for example, if you look at this one here, 4.3% carbon at 1147 degrees Celsius. This is eutectic reaction. Yeah. So we have liquid phase become austenite, gamma austenite phase plus Fe3C. Okay, two solid phase. So one liquid becomes two solid phase. That's eutectic phase. Yeah. Eutectic reaction. Yeah. And then if you look at this one at 1493 Kelvin, this point here, this is liquid delta phase become gamma phase. So liquid plus delta become gamma phase. So this is peritectic. Okay. So we have eutectic reaction, peritectic reaction. And then if you there's another invariant reaction here. So now gamma austenite phase become alpha ferrite phase plus Fe3C carbide phase. So it's one solid become another two solid phase. So it's a eutectoid reaction, yeah? Is that okay? So just inside the one phase diagram, we have three different actually the invariant reaction. It's a very actually, there's the some phase diagram, some very complex phase diagram which have the many actually the invariant reaction, but very simple binary system, but you have at least three invariant reaction contained. And that's iron carbon binary system, okay? And also one of the reasons why people are interested about iron, let's say, among the many different actually the base metals like iron, aluminum, magnesium, titanium, and etc. Iron is the most interesting actually material because iron itself have the phase transformation. Okay, so iron at low temperature you have BCC phase, intermediate temperature you have FCC phase, and then it become again BCC phase just before the melting, and then it melts. Yeah, so they have the three solid transformation. So and then also if you are adding like carbon, that actually the phase stability region of the BCC or FCC is changing a lot depending on the carbon concentration. So for example, when you add a carbon, so for example, if you look at this one, so BCC alpha phase is up to 912, and then it becomes gamma austenite, the FCC phase, yeah? And then when you add a carbon, stability region of the gamma phase is increasing. So it actually even going down to actually its original transformation temperature, yeah? Is it okay? So we call that actually, especially in the steel business, carbon is austenite stabilizing element because austenite actually area carbon. Okay, so this is interesting. Look at the iron silicon binary system. Silicon, when you add the silicon can go to the BCC phase and it actually extends the area for the BCC phase. So in this case, BCC is the alpha or ferrite here, and alpha ferrite or delta ferrite. So silicon is the BCC stabilizing phase or ferrite stabilizing stabilizing element. So when you actually design the alloys, especially for the steel, if you know what kinds of element can stabilize which phase, so is it austenite stabilizing element or is it the ferrite stabilizing element, depending on actually the fraction of this kind of element, you can design kinds of phase transformation. You can actually, control the phase transformation with a different mixture of this kind of element. Okay. Of course, the degree of the effectiveness for stabilizing each phase is depending on the actual element. Okay. So it's highly depending on the element. But at least from the phase diagram, we can already easily understand. Okay, which element is the stabilizing element for the austenite, and which element is stabilizing element for the ferrite. Okay, let's look at some of the cross views. So we talked about this one already. So now let's look at this one. So this is transformation, the microstructure change. Okay. So when you have, for example, about 0.7, 0.75, 0.8% of the carbon in the iron, and then if you increase temperature above 727, then you have single phase, gamma austenite single phase. Yeah. So if the single phase, you have to put this one at about, especially for the gamma phase, then according to phase diagram, you can increase temperature above 727 and then wait for a long time at that temperature. Then your microstructure will become eventually as a single phase. It's gamma phase, gamma single phase. And of course, when you talk about the single phase, it's different from single crystal. Okay, single crystal is, in your matrix, there is no grain boundary. So single phase without grain boundary, we call it single phase, single crystal. Okay, but when I talk about the single phase, it means there's only one phase, but that phase have the multi-crystal. Okay, so we have still grain boundary. So we have gamma austenite single phase area above this temperature. So all this area here is gamma austenite single phase area. So let's take actually this one, A. So let's assume we have the gamma single phase area here. And then if you cool it down below this eutectoid temperature, then what kind of microstructure can be formed? Then if you look at it, gamma become 100% become alpha plus Fe3C phase. Yeah? So we have two-phase mixture by the eutectoid reaction. So all this gamma will dissociate into the two-phase, and alpha and the Fe3C phase in this case. Yeah? And then typically, as I mentioned, kinds of lamellar structure because of limited diffusion in the system. Now, let's look at the other two cases. So this is exactly at the eutectoid composition, and this is the below the eutectoid composition. So we call this one, especially this actually the composition as a hypo-eutectoid. So you have exactly at eutectoid composition. If you are below, we call it hypo-eutectoid composition. So at the hypo-eutectoid composition, of course, if you increase temperature reasonably high, then you can have a gamma austenite single phase microstructure like this. And then if you now cool it down, then you go to the two-phase region, where it's the gamma and the alpha combination. And this is the kind of the microstructure we can expect, which will be developed from the gamma austenite. Because we have gamma austenite single phase with grain boundary. When you cool it down, the area, the alpha phase have to start to form, but alpha is not forming in the middle of the gamma phase. Typically, it forms around grain boundary. Because grain boundary area is high energy area, because of the mismatch of the atoms. Grain boundary is typically high energy state. Okay, grain boundary have the high energy state. So when you actually form the new phase, you need some activation energy, and you want to decrease the energy of the system. So by forming the actual new phase on the grain boundary, you can actually easily reduce the energy of the entire system simultaneously. So it's a high energy state area is the area typically new phase can be formed. Okay, so that's why alpha phase is start forming on the grain boundary first. If you cool it down, so alpha phase should be more and more. It should form more and more. So entire grain boundary is kind of decorated in this case by the alpha phase. Okay, and of course, if you say, okay, then is there any alpha phase can be formed inside of gamma? Yes, there is, but alpha is preferred to form on the grain boundary, but it doesn't mean that there's no alpha phase inside of the gamma phase. Okay, so it can form, but preferably it prefer to form on the grain boundary. That's what I meant. Okay, and then if you now decrease temperature below this eutectoid, okay, so all this alpha phase was formed. Okay, and then now when you actually decrease temperature here, then so you have this alpha phase and this austenite phase, yeah? So this ferrite phase, this austenite phase. If you decrease temperature, this one doesn't have to be transformed, yeah? This one is the pre-existing alpha phase, it stays as it is, and then this gamma phase should be disappear. Okay? So the gamma is dissociated into the now alpha and the Fe3C phase. So this gamma, pre-existing gamma phase, is start to make a phase separation into alpha and Fe3C. Can you understand the development of microstructure? So this one, so here, and as you can see here, called this kind of gamma phase, which is formed before the eutectoid reaction as a pro-eutectoid alpha phase in this case, and then all this alpha and the Fe3C combination, which is formed during the eutectoid reaction, is kind of, and we call it eutectoid alpha phase and eutectoid Fe3C phase. And this kind of shape, the kind of lamella shape in the solid state, we call this one as a pearlite structure. So it's just the naming of this kind of microstructure. Okay? So this is most precise way to present actually evolution of the microstructure from the high temperature to the lower temperature. Okay? You good? So it's kind of sometimes it's very difficult to say exactly how does the microstructure should be changed, but in this case, considering the grain boundary energy, in order to actually reduce the energy of the system, alpha is start forming on the grain boundary. That's actually the first thing you can think about. And then once everything is finished, then gamma should be disappear suddenly. So gamma should be transformed by itself into the alpha plus Fe3C by making this. Okay? So if you look at really the microstructure of the one-of composition like that, it looks like this in the end. So by end of this process, if you look at about that F position, this is one-of microstructure here. Okay? So all this white area, you can expect this is pro-eutectoid alpha phase in this case. And then all this black and white, actually the layer, actually structure, lamella structure, right, of the alpha plus Fe3C phase. Okay? So this is typical optical microscopic image. Yeah. Yeah. So if you start from here and going up, it's a very difficult question. Is it going to be a reversible process like this? No. It's very difficult to say. Yeah. The phase fraction is very easy to actually quantify. The total phase fraction is easy to actually quantify from the phase diagram, because it should be in the Leber rule. You should follow the Leber rule. But as I mentioned, the microstructure change, the image of the microstructure, it's rather difficult to really tell. Okay? And so, for example, if you anneal actually this one for a long time, is it going to keep this microstructure? No. Eventually, alpha want to become old alpha. So this lamella structure may not be remaining like this. This pearlite may not be remaining like this. If you have the pearlite structure like this, you have grain boundary in each of this area. Yeah? You have a very high energy state, in fact. So if you can actually make a diffusion, if this one is combined with this one, this white will be combined with another white, then you can reduce the grain boundary. So the total energy of the system can be decreased, still decreased, by forming bigger alpha phase and the bigger Fe3C phase. Yeah. So this will be changed with the time too. so when actually, so for example, when I ask you, okay, in the final exam, so draw the microstructure change. The only thing I can really take from your answer is, okay, what's the phase fraction? from the level. The shape, it's up to you. It's impossible for me to really say this is wrong or this is correct. Because, I mean, there's no time variant in the microstructure. And so I can say I'm cooling, but I mean how fast you are cooling, I didn't quantify. So how can I actually tell you how much actually grain is growing with the time? So it's impossible, yeah. But at least according to the thermodynamic, at least we are considering thermodynamically equilibrium condition. So at least I can tell you, okay, the phase fraction at least should be correctly read from the phase diagram by using the level rule. That's the only thing I can tell you. And the microstructure in general, it looks like this, but when you actually heat it up, is it going to be just reversible like this? No. Case by case. Yeah. Yeah. Composition should be same depending on pro-eutectic or eutectic, eutectoid or pro-eutectoid alpha phase have to have exactly same composition. So at this point, the pro-eutectoid and the gamma is different, but when you actually cool it down, the pro-eutectoid alpha phase and then eutectoid alpha phase should have exactly the same composition. The phase fraction, of course, if you're just considering in this way, the amount of the pro-eutectoid can be already determined here, and then the amount of the alpha phase inside of the eutectoid can be determined from this one to cooling down. So you can actually find fraction of the pro-eutectoid alpha phase, okay? But the composition should be read from the phase diagram. Okay? So if you actually cool it down further and further, the alpha phase composition is changing, yeah? And so this alpha phase composition should be changed continuously, simultaneously with these two, both of them. When you're doing this, probably the Fe3C phase fraction is slightly increasing with the decreasing of temperature. Yeah? Okay? You good? Now, let's look at the other side. This is hyper-eutectoid. So we are in that eutectoid composition, then we call it hyper-eutectoid. So hyper is below, hyper is above. Okay? Probably you heard about this kind of terminology in your introductory course in the material engineering. So hyper and hyper. So this is hyper-eutectoid. So let's start again from the G, this point here. So we should have single gamma phase. So same as the actual. So we have single gamma phase actually, microstructure like this. And when you cool it down at this point, then now we have gamma plus Fe3C, two-phase region. So Fe3C start forming on the grain boundary, like the previous one, for the alpha actually forming on the grain boundary. So second phase is start forming on the grain boundary to reduce the energy of the system. And then when it's cooled down below this eutectoid reaction, then all this probably, if you have enough actually the Fe3C is forming, all this grain boundary is decorated by the Fe3C phase first, and then the remaining gamma phase is dissociated into the alpha and the Fe3C phase like this. So grain boundary area is different phase, yeah? So previous one, grain boundary area was occupied by pre-eutectoid alpha phase, or pro-eutectoid alpha phase, and this one is decorated by the pro-eutectoid Fe3C phase. Okay? And then if you look at that term microstructure, it looks like this. This is totally, it's very difficult to understand, yeah? Now, here is Fe3C. Black is alpha phase. The previous one, white was alpha phase, and then black was the Fe3C. How come? I mean, why the color is changing? This is because we are using optical microscope. In the optical microscope, we cannot see actually the color of the phase. I mean, there's no way. the optical microscope just show you actually some kind of etch. So when you do the etching for to see the microstructure, that etchant just try to actually the etching, different amount on the surface for the alpha and the Fe3C. And then if you have sample, depending on how you actually rotate your specimen, one part become more darker and one part become more white. You cannot tell which one is which one in the optical microscope. Okay? So that's why it looks like, white, in this case, white is alpha phase, the Fe3C, and black is alpha phase. But previous one was, white was actually alpha. And so it's really depending on how you actually tilting your sample. Okay? But if you now look at this kind of specimen under the electron microscope, now it's a different story. Because electron microscope is not merely looking at actually the corrosion of the actual surface. It's etching, the kind of the height of the actual surface of the two phase, and it's really looking at now the activation energy from the activation of the electron on in each phase. So you can actually see the more dark area, more white area, depending on how much actually the exciting of the electron from the two different actual phase. Okay. Typically, when you have more white, so if you actually look at the electron microscope, typically when you have the more heavy element, become more white, okay? And black is more actually the more light element phase. Okay, so we talk about this one. So this is the Gibbs energy and the activity actual relationship. So we say that when you have any kind of the composition in this Gibbs energy diagram, then if you draw the tangent line, we know the partial Gibbs energy. The difference here is the RT lone activity like this, yeah. And so partial Gibbs energy is, you can assume that it's almost same as the chemical potential. Okay, strictly speaking, it's a little bit different, but I mean, in this course, you can assume this is same. And so, let's look at this kind of condition. So when you have, for example, about 0.8 mole% of the B and 0.2 mole% of A at this temperature, then you have the pure B plus liquid is coexisting. And according to the Gibbs energy diagram, it should be looks like that. So you have liquid phase, which have the Gibbs energy curve from pure A liquid to the pure B liquid, as you can see here. And then you have the B solid phase, and then the cotangent line of this pure B and this liquid phase should meet at the 0.6 for the liquid area. Then you can have the liquid 0.6 B in the liquid and then pure B in the solid phase, and that actually coexist together at this temperature. So this is kind of the liquidous line of B solid phase at this specific temperature. Okay? And we talk about this one. So now, Gibbs phase rule. So let's look at this one. This is interesting. So Gibbs phase rule is useful when you construct a new phase diagram. Okay? So especially when you have the very complex, when you are doing the experiment to really find out the phase diagram from the experimental actual measurement, sometimes it's very difficult to distinguish, okay, whether I have single phase here, two phase here, or three phase here, okay? But according to the Gibbs phase rule, you can easily tell, okay, whether I'm making the mistake when you're constructing the phase diagram or not, okay? So Gibbs phase rule is just equality of the different kinds of the thermodynamic property in the system. So let's just consider this way. So let's assume I have a given system which have P number of the phase. So I have 1 phase, 2 phase, 3 phase, and etc. So I have up to P number of the phase. Okay? And then let's assume I have C number of the, C number of the component. So so if I have AB system, I have 2 components. ABC, I have 3 components. ABCD, I have 4 components here. So when you're actually considering the C number of the component in your system, and you can, so how many number of the phase I can have in maximum in the given system? That's actually Gibbs phase rule. Okay? So if you look at actually the thermodynamic, from the thermodynamic point of view, So the temperature of each phase should be same at the equilibrium condition, yeah? And you have AB binary system, and if you have two phase, phase A or phase FCC or phase liquid should have exactly same temperature. Yeah, so at the given temperature. Given temperature, two phase, both of the phase have the same temperature, okay? So when you have two phase, you have the one equality of the temperature equation. The page number 1, page number 2 have exactly the same temperature. And if you have three phase, page number 2 should be same, page number 3 should be same. Then automatically page number 3 and page number 1 should be same, yeah? That's automatic. So independent equation for the temperature constraint. Then if you number of the phase, you can have P1 number of the equality equation for the temperature. Okay, good? So that's the temperature constraint for the equilibrium. And now pressure is same, yeah? So pressure component number 1, pressure, page number 1, page number 2 should be exactly the same pressure, and etc. Then you'll have P minus 1 equality equation for the pressure. So this P is the pressure, okay? And now we are going to the activity, or Gibbs energy, okay, partial Gibbs energy. So I have I have FCC phase and liquid phase, as I showed you before, okay? Equilibrium condition, partial Gibbs energy of A and partial Gibbs energy B should have some relationship here. A is solid, no. The A phase is the same component in the two different phase. So I have FCC phase and I have liquid phase. Then A in the FCC equal to B, A in the liquid phase. And then we can make a chemical reaction. At equilibrium condition, delta G naught of this one equal to minus RT ln activity. So there's a relationship between activity in the A in the FCC phase and A in the liquid phase, yeah? Am I right? So that's the kind of activity, kind of relationship. So phase number 1, alpha phase, so I component, no, yeah. I component in the phase number 1 and I component in the phase number 2 have some relationship. If both of them is solid and the same structure, then this and this activity should be same, yeah? If this is FCC, this is BCC, there is some sort of the correction term, but we can make an equation between the activity in FCC and activity in the BCC, or activity in the liquid and etc., yeah? For the given component, okay? So if you number of all the P number of the phase, then we can have P minus 1 number of the equality equation for the activity for the component I, and then activity component J, and etc., and etc. Okay? So if you look at all this equation, then total number of the equality equation is, so P minus 1 times up to component C. So this C number of the component plus P pressure 1 and the temperature 1. There's two more, yeah? So it's C plus 2 times P minus 1 equality equation can be generated from here. So this is number of the equation we can make. Okay? To make actually this given system is in equilibrium condition. And then, now number of the total number of the unknown variable. Okay? Then we can see, okay, so here, so this is, so variable here, 1, 2, 3 to the P times C plus 1. Why C plus 1 instead of C plus 2? So this is C and then 1 and 2, C plus 2, yeah? But it becomes C plus 1. This activity eventually containing the composition inside there. So if you have 10 component, 9 component composition is fixed, then the last one can be automatically fixed by 1 minus sum of the rest of the component for the given phase. Yeah. So composition point of view, you is one number of the variable, and 2 temperature and pressure is total actually the unknown variable under the P different phase. So P times C plus 1. So this is total number of the variable So unknown, basically, this is total number of the equation I can generate to make actually this is equilibrium condition. So freedom of the system equal to total number of the variable minus total number of the equation. Okay? Then if you do all this actually, if you just do the mathematics here, freedom becomes C number of component minus number of the page plus 2. Eventually you can get this one. So that's why freedom F equal to C number of component in the system minus number of the page plus 2. So this is so-called Gibbs phase rule. So this tells you that how many phases can coexist at the given number of the component of the system. So, for example, if you have binary system, so I have two components here. So equal to 0, that's invariant reaction. So when F equal to 0, I have C 2 minus P plus 2, so P should be 4. So it means I can have maximum 4 number of the phase when the freedom equal to 0. So when freedom 0, it means there's only single point which actually meet that condition. So it's kind of eutectic composition, eutectic reaction. But in the system so far, we see liquid become too solid. So there's 3 phase, yeah? That's when you actually have freedom equal to 0. But according to the Gibbs phase rule, F minus C plus P plus 2, then F when F equal to 0, C 2 minus P plus 2. And then under that condition, P should be 4. And so far, the phase we've seen is only 3. What's going on here? So general Gibbs phase rule, we consider there's the change of the pressure. Yeah. So pressure is not, pressure could be the variable, one of the variable. So when we actually really see the PT and then component system for the binary, you can have maximum 4 phase can exist together, even considering the pressure variant. Okay? But if you actually stop the pressure, I say pressure is constant. These 2 here, one of them is temperature, one of them is pressure actually variable here. Okay? So when you say I have constant pressure condition, then this Gibbs phase rule become F equal to C minus P plus 1. That's usually what we are using the most of the time. Okay? Then when F equal to 0, maximum number of the phase in the binary system is 3. That's all the invariant reaction actually. We can see it in the phase diagram. Okay? Eutectic, eutectoid, peritectic, all this one involving 3 phase. And that is only existing at the one specific condition. Okay? So now actually let's look at this. Let's consider this kind of phase, Gibbs phase rule, and let's look at this phase diagram. So this is the for single component system. So like H2O. Okay, so we have ice, and then we have liquid, water, and then we have vapor. 3 phase, yeah? So something like that. And so let's assume this is single component system under the PT, actually the phase diagram. So it means F equals to C minus P plus 2 in this case, because we have both temperature and pressure is considering as a variable. Okay? So when freedom equal to 0, F equal to 0, maximum number of the phase is 3. Am I right? We can have 3 phase existing together in this PT diagram. So when you look at the water, we have a triple point. Yeah, solid, liquid, gas is existing together, triple point. That's invariant reaction basically. Okay, equal to 0. So when we're actually doing this kind of the actual phase diagram study by experiment. So let's assume this way. So I have this temperature, I'm having this pressure, and then I try to find what kind of phase is forming here. Yeah. So this is alpha phase region. So even I change the pressure, I change the temperature, or I change pressure, temperature, I have same phase. That's why it's 2 variable can be moved for the single phase. So it's freedom equal to 2. Why? F 1, and then if I have one component, then F equal to 2, freedom equal to 2. In this case, the freedom is temperature and the composition. Temperature and the composition. Pressure, sorry, temperature and pressure. There's no composition variable here. It's a single phase. So all this single phase area, you can change temperature and the composition, temperature and the pressure, but you can still have same phase. That's the freedom means. Okay, how many variable I can change by keeping the same phase, same number of the phase, same assemblage of the phase. And then if you look at this line here, this is phase boundary between alpha and the delta. Okay, so I mean theoretically under this line you have both phase existing, two phase existing in this line, on this line. So F equal to C minus 1 minus 2 plus 2. So F equal to 1. Freedom equal, because you can have, I mean, you can change the temperature, but if you change temperature, pressure is automatically changing. So pressure is depending on the temperature. And if you change the pressure, temperature automatically changed by the pressure, I mean, temperature should be changed accordingly to have two phase. So the freedom under this line is 1. And then when you go to this triple point, three phase existing, then F becomes 0. So that's the maximum number of the phase. But when you do the experiment like this, so you have one phase, one phase, one phase, one phase, one phase, and then suddenly at one point you feel like there's the four phase existing. Okay? But according to the rule, for the single component system, you can, okay? There should be three triple phase around here. So probably this will be something like this, and then there's another line, another line. So there's one triple point, one triple point, one triple point. But because that three triple point is very, very close to each other, then experimentally you see that it looks like a four phase region, but according to the Gibbs phase rule, you cannot have four phase region. Okay? So Gibbs phase rule to find out how many maximum phase I can have at the given system. Make sure that you are not making actually the phase diagram, you are not make any mistake when you actually construct phase diagram. Okay? So this was same. So for the binary system, let's look at this one. F equal to C minus P plus 1, because I say it's constant pressure. Okay? When it's constant pressure, the last two become 1. Okay? The last actually, this variable 2 become 1. We fix the pressure, okay? So, in the binary system, two component system, when you have this single phase region, like liquid phase, so F equal to 2 minus P, number of the phase is 1 plus 1. So it means F equal to 2. So Y is 2, composition over the B, and then temperature. So when you change the composition B, composition A is automatically changing. So it's one variable. And then temperature can be still changed, but you can still have the same phase. Okay? Now, let's go here. This is two-phase region between this one, LICL, no, this is KCl, and this is LICL solid. We have in the two-phase region. So if you actually look at this phase diagram, so Gibbs phase rule, F equal to C, 2 minus 2 plus 1, F equal to 1. Freedom is 1. Why is freedom is 1? I can change this way and this way, yeah? It looks like 2. Isn't it? It looks like 2, yeah? I can change this one and this one because this is area. But changing with the composition doesn't change anything. Changing with the composition here, change the amount of the two solid phase, yeah? But it doesn't change the composition of two solid phase. Composition is same, yeah? With even you change the amount of the LICL here, the composition of the two solid phase is still same. The relative amount is changing by the level rule. Am I right? In the thermodynamic world, the amount is not important. When you look at the Gibbs phase rule, we didn't consider the amount of each phase. We consider activity or the composition of the phase and temperature and the pressure. So the amount is not important in the Gibbs phase rule. Okay? Amount is mass balance, that's it. And it doesn't really reflect any thermodynamic property, any partial property. Of course, total Gibbs energy can be changed depending on the actual amount of each phase. But according to on the inside of Gibbs phase rule, we don't consider actually the amount of the different phase, only the composition and the temperature and pressure. Okay? So this composition variable is not really effective here. Okay? Only temperature. So even you change the temperature, you have same phase. Okay? So temperature is still variable. Same thing here. Composition doesn't change anything, only temperature. And now if you are on this line, you have three phases. So for example, at this point, you have 1, 2, 3 phase. Yeah? So there's only single condition which have three phase. So that's F equal to 0, invariant reaction. Okay? This is how we have to apply the Gibbs phase rule. Okay. Now let's look at this one. So this is the single component system. So single component system. This is with the phase diagram for the pure SiO2. So the SiO2, probably the glass, typical glass, is about 70% or 80% of SiO2. And then there's some additional element like CaO and MgO and something else, okay? But pure SiO2, even for the pure SiO2, there's the total 9 different kinds of the crystal structure. Can you believe it? SiO2 have so many different crystal structure, depending on the temperature and depending on the pressure. So, in the temperature wise, at the room temperature, we have so-called low temperature quartz phase, high temperature quartz phase, low temperature tridymite, high temperature tridymite, low temperature cristobalite, high temperature cristobalite. There's already 6 solid phase plus liquid phase, 7. And then with the increasing of the pressure, you can see that this beta quartz is actually high temperature quartz phase, is stabilized, and it transforms to another completely different phase, quartzite, and then there's one more, stoichiobyte or something. There's another solid phase existing, even at the high pressure. Okay, so it's changing. It's the phase crystal structure depending on the pressure as well. And typically, when you increase temperature, the solid phase, when you increasing pressure, the melting temperature of solid is increasing. Okay, because when you actually give the pressure, everything wants to become, the crystal, the atomic distance become shorter and shorter, yeah? So, it have the more, it will make more solid phase than the liquid phase. Because you are packing the atoms, it tries to make more solid phase than liquid phase. So, typically when you increase the pressure, solid melting temperature is going up. Sometimes actually it's going down, as you can see it's going down. Because when you actually increase the pressure, this beta cristobalite has very interesting structure. When you increase pressure, its volume is increasing. Most of the case, when you increase the pressure, the volume should be, because it has the more packing. But when you have crystal structure is certain arrangement, when you increase the pressure, actually molar volume is increasing. That's actually very strange, actually, the crystal. One of them is even SiO2. Anyway, so when you have this kind of thing, actually this is the one of the paper I co-authored with my friend who was in geology at the time. So here actually look at this solid liquid, the two phase actually the region here. It's a very high pressure and then very high temperature. And then in order to actually put the sample at that high temperature, he needs the uranium capsule. This is uranium metal. Because at this temperature, most of the metal is melted already. It's 2,400 Kelvin. Most of the metal is already melted. So he have to use the uranium kind of sheet, and then the SiO2, and then put it to the high temperature. And then he did the temperature here. This is very lucky case. He see the two solid and liquid together. It's almost impossible because you have to know exactly what's the temperature. Okay, so he found two. And when you look at EPMA, under the SEM, electron microscope, the composition is exactly the same because both of them is pure SiO2. The only way you can actually distinguish these two is by using the XRD. So you have one is glass, kind of the amorphous phase. The other one is crystalline phase. You see that peak and then very broad peak and the very sharp peak together. Then you can say, okay, this is two-phase region. And this is the real phase diagram for the very high pressure. And this kind of phase diagram is studied a lot by geologists because in order to understand, okay, where this rock came from. So when you have any volcanic movement, volcanic actual kind of activity, geologists go there first. Try to take any rock sample coming from actually the volcano. So some of them is, most of them is lava, but when you actually have this volcanic actually reaction, there's some rock is really coming out from the earth, deep earth. And when you actually take that sample, they analyze that and then they calculate what kind of phase is forming, what's the actual composition of the distribution between different phase. Then from that information, they can actually find where this rock came from, how deep of this, the magma, how deep is this actually the volcano is started from. That actually can be told from the crystal structure and also the composition. And this is also another actually the example for the phase separation. Now, as you can see here, this is liquid phase, this is liquid phase, and this is liquid phase. So you have here liquid immiscibility. So liquid miscibility. So two liquid is not miscible each other. So when you actually make a sample here, if you heat it up, then you have this liquid phase, which looks like this. Okay. So in this case, even you use the XRD, now you cannot tell there's the two phase. Both of them is amorphous. So under the XRD, you cannot see it. There's no crystal structure. The only way you can tell now two different phases by using the EPM, the electron microscope. Then you can actually pinpoint the composition of each phase and then find out there's actually two different compositions. Okay. And also, if you're doing the etching, because the composition is different, the reaction with the etchant is slightly different. So you can see it like little bit actually different kinds of the color between the two. So two liquid phase in this case. Okay, this is another type of phase diagram. So far we see the actually pressure temperature phase diagram and then temperature composition diagram. But we can also see this kind of phase diagram as well. So this is the nickel cobalt binary metallic system, and then if I applied oxygen, how does that actually the system can be changed? So when you add oxygen, you can make oxide here. So nickel oxide and cobalt oxide. And nickel oxide and cobalt oxide make complete solid solution, FCC solid solution. And nickel metal and cobalt metal also make a complete, I think, FCC solid solution as well. But one is oxide, one is metal, yeah. So, for example, we did something like this for your one of the homework, iron manganese system, and then when you actually have a certain partial pressure of oxygen, what would be the final manganese content in the metal? What is the final manganese oxide content in the oxide? Do you remember that? Okay. So, let's assume I'm putting nickel and cobalt under the partial pressure 10 to the minus 10 atm. Partial pressure of oxygen 10 to the minus 10 atm. So this diagram can give you the answer directly. So this is nickel, cobalt, and this is at one temperature, 1100 degrees Celsius, fixed temperature. If I increase the partial pressure of oxygen in the system, whether this metallic phase existing as the metal, or this metallic phase becomes solid, oxide, or solid and the oxide and the metal. So for example, let's take a 0.5. If I increase temperature, if I increase the partial pressure of oxygen, it starts to become oxide, more and more oxide, yeah? So above this partial pressure of oxygen, now I'm in the two-phase region. So metallic phase region and oxide phase region at the given partial pressure. So for example, if I take 0.7, I'll have at this partial pressure 10 to the minus 10, then I'll have this metallic phase, because this is metallic phase, and this oxide phase. Okay? So the composition of the metallic phase will be about 0.48 cobalt and 0.52 nickel, and composition of solid oxide which is forming at that condition is 0.85 cobalt oxide. So this is cobalt nickel ratio. So even in the oxide phase, you have cobalt oxide, nickel oxide, cobalt oxide. Yeah. So this one is 0.85 cobalt oxide and 0.15 nickel oxide. So this can exist together. So we can do the thermodynamic calculation, or if you have this kind of phase diagram, you can already see the answer. Okay? So when you have this kind of, so 0.5 composition, if I want to make all this metallic phase become oxide, what would be the lowest partial pressure of oxygen? Then I can increase and increase, and above this one, everything become oxide. So lowest partial pressure of oxygen, which make everything become oxide already, is this partial pressure. So that is about 10 to the minus 9.5. Okay? So this is one type of phase diagram. This is three component, nickel, cobalt, oxygen, 3-component system in fact. And this is another phase diagram, another type of phase diagram. So both axis is now pressure. Okay, so I have metal, iron, sulfur, oxygen ternary system at 1100 degree Kelvin. Okay, and so I mean you cannot actually present your metal ratio in the x-axis here because there's only one metal. And sulfur and oxygen, both of them easily make a gas phase. SO2, SO3, SO, all the gas phase, sulfuric oxygen gas phase, and then, or you can even make S2 gas, and then oxygen, O2 gas. Okay? So in this case, 2 axis is the partial pressure of gas phase, O2 and S2. And then we put the ion into the system at the certain partial pressure of oxygen, certain partial pressure of S2. Then what kind of phase can be formed? That's this phase diagram. Okay? So for example, let's assume I'm putting ion at 1100 degrees Celsius under the partial pressure 10 to the minus 15. So I'm looking at this position here. Okay? And then also I'm controlling my partial pressure of sulfur 10 to the minus 15. Then this is the position I have to read. Then if you put your ion in this condition, you'll make Fe3O4 phase eventually. So no sulfide phase, only oxide phase can be formed. And if you decrease, then you can even make iron metallic phase. There's no sulfide phase. If you increase it, sulfur actual partial pressure, you can make FeS solid phase as well. Okay? So this phase can be read in this way. This kind of your original mineral phase. So for example, when you do the processing for extracting the metal from the mineral, so mineral originally can be sulfide or oxide, whatever it is here. So let's assume I have original mineral, Fe2O3. Okay? And then there's a little bit of sulfur inside of my system as well. So if I put this one into the furnace, how should I control my partial pressure of oxygen? How should I control my partial pressure of sulfur to make my Fe2O3 become already FeO, for example, without making FeS? Then so this kind of diagram is very useful for the treatment for the mineral phase or intentional oxidation or sulfication of the actual phase as well. And especially this diagram, we call it predominance diagram. So predominance diagram is phase diagram which is consists by the 2 different partial pressure of the gas. That we call it predominance diagram. Okay? Or stability diagram is saying predominance diagram. How we can draw this kind of diagram then? I mean, thermodynamically, we can draw this diagram in this way. So for example, this boundary line here, this boundary line is phase boundary between FeS and Fe3O4. Yeah? So under this, on this line, you have these 2 phases exist together. So FeS, Fe3O4 should exist together under given condition. Okay? So we put these 2, and then we know axis, which axis we want to use, then we put those two gas phase in the each side of this chemical reaction. And then at the equilibrium condition, it means all these four existing together at the equilibrium condition, yeah? That's equilibrium, okay? So we put we make a chemical reaction intentionally to have both phase from both phase existing on this boundary, put both of them in the each side of this chemical reaction, and then distribute your gas, actually the component in each side of this chemical reaction, and then make that chemical reaction become equilibrium state. Then delta G equal to 0, so delta G naught equal to minus RT ln constant. And equilibrium constant is consists of the Fe3O4 and FES, and then partial pressure of SO2 and partial pressure of S2. So both these two phases, pure stoichiometric phase and activity equal to 1, then you can find the relationship between the two different partial pressure. Yeah, that's how we actually calculate it. Same thing for all the other phases as well. Okay, so phase boundary for this kind of stability diagram, predominance diagram calculated by this one. So when I was a student, actually, we were doing homework like this, draw predominance diagram of something, by doing all this chemical reaction calculation. But I mean, you don't have to do, you have to understand how to do it. That's more than enough. Same thing for the copper. So this kind of diagram, copper diagram, is very important for the copper smelting process. So when you go to the, for example, LS Nico, the copper smelting company in Korea, they are using this kind, they are using many of this kind of diagram for the pre-treatment of their mineral and also production of the actual liquid copper in the end. Okay, so that's more than enough. And nanothermodynamic, you don't have to worry about it. This is not part of the actual your exam, okay? I just want to show you, okay? There's another extreme of the thermodynamic, and that's actually the size dependence, but I think I don't want to really talk about this one. Okay, so that's about it for the thermodynamic course. So we have done, I don't know, like 3 months, and I hope this course this course gives you some interest about thermodynamic. And thermodynamic, the final exam number 1 is always same. So you'll have 10 points. Prepare very well. It's not for your grandmother, it's my grandmother who don't have any PhD in the thermodynamic or chemistry, okay? So you have to really explain. Very simple word. Not any equation. If you have any equation inside of question number 1 answer, you're going to have 0 mark. Don't explain anything with the equation. Explain very simple word, something which is, for the something related to your living life and the daily life thing. Okay, that's actually best. Okay, so that's the first part of thermodynamics. So first row, second row, third row of thermodynamics. So you have to explain this one, very easy word. And then we're done like enthalpy. I love enthalpy. Enthalpy is very important. Yeah? It's energy balance. So whenever you do any, the material process design, you have to always consider energy balance. Because energy is the money. Heat is money. So you're going to see definitely you're going to see actually the one question for the heat balance calculation. But I'm not going to actually ask you to do a very simple case like we did in the midterm number 1. It was not simple, but that's only involving pure solid phase. Yeah? We're going to have more complex system. Because we know now solution, regular solution, ideal solution, and all kinds of things. And so all this actually knowledge should be combined together to do the heat balance calculation. Okay? And then we did all this, sometime I'm asking you, okay, whether my reaction is going to the forward or backward. So you have to really read your question very carefully, whether I'm asking you equilibrium condition or I'm asking you the direction of the chemical reaction. Okay? Most of you now understand, how to distinguish these two, but you have to know how to distinguish it. And then once you distinguish it, you have to also answer very well. Okay? Whether it means left side or right side. Because sometimes you did the calculation and then you are not making the final answer very clearly whether this means my direction is going forward or backward. Okay? So like the question we have done in the midterm number 2, I ask you, okay, so I have this kind of the calcium content metal in the magnesium. Can I get it or not get it? You did the beautiful calculation, delta G equal to blah, 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 and then this is positive or negative, and then you cannot make the final decision. So this means I can make it or I cannot make it. That's actually your decision, yeah? You have to make it. You have to make a final decision. So when you actually make the final decision, be careful. So understand, okay, what is actually the real mean of this kind of delta G, okay, positive or negative. And we did a lot of this, the Hennian solution, solid or liquid solution, Hennian activity coefficient. I love Hennian activity coefficient, okay, because this is very important for the many metallurgical system. So we did like some Hennian solution with the liquid, nitrogen in the liquid metal. And so I'm going to change some of those style to a little bit more complex. And even I may ask you to draw some diagram or something, I don't know. I think about it, because I haven't prepared actually my final exam yet. But I'm going to prepare tonight or tomorrow morning. Okay? And then reading the phase diagram. So in the end, I mean, you know that phase diagram is directly connected to the Gibbs energy. Okay? So you have to really understand this relationship. Okay? So at least you're going to see, I believe, at least you're going to see more than 2 questions for the phase diagram. But not just phase diagram. You have to understand how to read the phase diagram to solve some question. Okay? So at least you have to know how to read the binary phase diagram. And one thing also I can tell you certainly is you're going to see the change of microstructure with the temperature or with the composition. Okay? Because that's your homework number 4. And one of those questions will come out for your final exam. Okay? So I gave you already 2 questions. Very first question, very last question. And the rest of them is mixed up. Okay? Fair enough? And homework number 5. I told you homework number 5 is kind of the summary of all your knowledge for this course. Because there, you have to calculate enthalpy, you have to calculate Gibbs energy, and you have to calculate melting temperature, even you have to calculate phase diagram from that. And then you can even calculate activity, yeah, from all this cotangent line, okay? So homework number 5 is very important. I'm pretty sure if you don't do your homework number 5 properly, you're not going to actually answer one of the questions. Final exam, one of final exam. So I'll make something to test whether you did your homework number 5 by yourself or not. Is that okay? Any question? No? How was course? Is it okay? My English was okay? Is it okay? Not very difficult, yeah. I don't know that. My English is not very good. I'm not using very complex word because I don't know. You good? Good enough? Okay, thank you very much for whole semester to participate in this course.